Hey, my name is Michael Blaine Hewling. I'm in lab section M06, and this is the following object lab. My observation was a falling ball of neodymium magnets, and the result I found was that the model in Python run with drag was more accurate to the real world than just that one run with gravity, and that the model with drag will also yield a terminal velocity. In the tracker video, I set the origins just at the ground where the ball hit. The ball is up in the positive y direction and it drops in the negative y direction. I've set the scaling to 0.05 meters using the diameter of the ball of magnets. And as you can see here, I tracked the ball all the way in motion until just before it hit the ground. And the whole length of this run took roughly 0.5 seconds to complete. Coming over to Python, we plug the ball's mass, which is 0.175 kilograms, in. We plug in its initial position, which is 1.55 meters in the y direction, which was gathered from the tracker data. We set a small delta t based on the runtime of the video, which was 0.5 seconds. We set our net force, which is going to end up being the force of gravity for this run, which is negative 9.81. And then by applying the Newtonian principles, our model looks something like this. As you can see, the ball starts and drops down to its final captured in position, and as time increases, the distance from the ground decreases. Now we're going to run the model again, except this time counting in drag. Drag is essentially the air resistance of the ball when it is dropped, and it works against the force of gravity. So when we run it, we can see that as the ball drops and reaches higher velocities, there's more air resistance on the ball, which will in turn slow it down more as it drops. When comparing the data in Tracker to that of the data gathered from the models, in the no drag run, you can see that the Tracker data in blue and the Python data in red actually line up very closely, which shows that the model is a good representation for what's happening in the real world. However, when you look at the no drag data, despite some of the points being off, they don't exactly line up in the end like they should. However, when you come over to the data that has calculated drag, though the chart looks very similar and it's still a close representation, you can see down here that the points at the end match much more closely. Now, though the red covers, you can look right here and see that at 5.434 seconds, it is 1.6 meters off the ground, and coming down to the bottom of the Python data, you can see that that number is almost the exact same compared to the no drag where it was not. So the drag run is a much more accurate case for the real world data. The what if question asks which models, if any, predict a terminal velocity. And the model that predicts a terminal velocity is the one that includes drag in the calculation. The reason this calculates terminal velocity is because at some point the drag force will become equal to that of the gravity force, and they will cancel each other out, creating a net force of 0 and allowing the object to travel at a constant rate. So when we come back to our model and we change the length of time that it is going to run and run it again so we can see it fully, as the ball drops, drag force increases, and at a certain point, the velocity at which it's traveling becomes a constant rate. The what if question wants to know, if an object is thrown downwards, does it still reach a terminal velocity, and if so, how does that compare to the terminal velocity from when it's just dropped? The answer is yes, it still reaches a terminal velocity. It just reaches the velocity at a quicker rate than one dropped without an initial force. The terminal velocities of both situations still stay the same though, because even if the power that it was thrown by was greater than that of gravity, the exceeded force would eventually cancel back down due to drag. And now, as you can see, the velocity changed in Python and the program run. It still reaches that terminal velocity where it's traveling at a constant speed. The only difference is it reaches it much quicker than it would have from an initial drop.